All right, welcome back. I got a couple announcements to start with. First, it's really cold, but we're here, so congrats. Warmth is on the way. But second, I got a little ahead of myself on the quiz, as you saw. Had a question about multiple imputation. Didn't really mean to put that there. Wasn't thinking clearly. So everybody's going to get all the points for it. Sorry about that. Multiple imputation is a distance part further away. I did create a homework too. I had originally said that it was going to be due February 28th, but in looking at the homework and looking at my schedule, March 7th, another week later. So got extra time. Okay. Um, and on that note, as we're going to talk about getting in today, the book itself, chapter 3, is an interesting chapter, wouldn't you say? And so what I've been struggling with is this lecture today of how am I going to integrate everything that's in chapter 3 that I think you should know about, in addition to telling you the background knowledge that you need to know about. And then toward the end of the chapter, I don't know about you, but it seemed like there was just model vomit that was just like just a mess of models just thrown up on the papers, on the pages. So I'm trying to come up with a way to organize all of that. So in that sense, chapter 3 is going to take a little bit of time, right? So your next reading assessment, I'm not going to give, but I have an assessment. It's like a miniature, it's like reading, but you have to sort of pick your own path. One of the things I'm realizing as I'm looking at chapter 3 in this book is, you know, the methods he's describing have this general sense to them, right? Oh, we got to worry about, maximum likelihood or Bayesian or missing it, multiple imputation. Those are the three big paradigms we talked about. But none of that tells you how to do it with your own model, right? And I don't know how many of you are going to have a model that fits into the things that you see in chapter 3 or chapter 4 or otherwise. And so what I thought to do was to start trying to get you to think about what uses for missing data might you have. And that's what the next quote unquote reading assessment is. I'm asking you to find a paper published in the last, I think, 20 years or so that said that has a set of analyses or an example analysis that you think you will need to know how to use with missing data. Right? The paper doesn't have to have it, but just that's the type. So what that will do is tell me what the analysis looks like. Then the second next step to that is asking you about take. So most papers, particularly empirical papers, have 4 or 5 different models. Pick one of the models and then provide the notation for it. All right. Now that's an odd task, but I mean that because what I'm going to turn around and do with that is once you submit it to me, is either I'm going to assign it or help you build it, both probably both. We're going to create simulation code that have data that look like you would need for a model like that. All right. And then with that data, we're going to then make it missing and make it missing at random. We can assume that we can build that assumption in, make it missing at completely random. All right. We even miss it not at random. Right. So what I'm trying to do is find a way forward where we, number one, know what the answer key to your data are, what the right answer should be, right? And if you have real data of your own, you don't know what those are, right? Number two, try to make it so that these topics that you read about in the book, which are somewhere between very general and overly specific, we sort of fit the gap between that, where you'll have this file, you'll have a data set that if it runs, you'll get a data set, it'll have missing data, and then you can use that in practice in this class to implement maximum likelihood or Bayesian or otherwise. So that's my goal to try to make after reading and honestly banging my head against the wall about how am I going to do this lecture today. That was what I came up with. So I'm kind of excited about it. We'll see how it goes. Um, if you're not familiar with simulating data, don't worry about it. I will help you build it. I will help you get it taken care of. If you're not familiar with notation, that's okay. I'll happy to help you with that as well too. But those are sort of the cornerstones of what happens. And the reality of it is I'm reading this, you know, chapter 3 introduced maximum likelihood with missing data and things like factored regression and structural equation modeling approaches. Well, I didn't get a sense from chapter 3. First of all, it's a really difficult topic to talk about, right? Missing data, because, my model that I like to use or my analysis that I'm going to use may be different than yours in your typical workflow or typical place that you look. So how do we come across with a strategy for missing data that fits both? I think my thought of that was we go with the high level. Okay, these are likelihoods. That's how they work. Teach you a bit about likelihood theory. Think about Bayesian. Think about like the high level stuff. But then there's nothing specific to your use case. So that's where I'm trying to fit that need. Thoughts on my approach? Comments? Suggestions? Anybody? Sound okay? So don't read anymore yet. The stuff in chapter 3, the background information, like when you get into the structural equation modeling approach, some of you've taken SEM before. Some of you've taken path models before, but you've never put it together and never talked about missing data. So I feel like I need to give you that background. But what I really need to give you is the conceptualization of why it works, what framework it fits into. And that's sort of what the lecture today is. And then, as I will note, there's no in-person class next week, and I'm going to tell you there won't be an activity either. Your activity is work on this reading assessment to find a paper, build a model, and report to me. Okay, or build the notation, report to me. This next step after today will be to sort of synthesize the SEM approach, the factored regression approach, how the EM algorithm might fit into that, and so forth. But today is more the background and big picture information. How's that sound? Okay. And this is no knock on the author. I think Enders is a good author. I think it just speaks to the nature of missing data problem, right? Everybody's analyses are incredibly idiosyncratic, right? But missing data applies some constant theory that's at a level that we normally don't teach, at least in the applied sciences. And so I'm trying to balance this too. We're going to talk about the level, like we're getting into likelihoods. Last week we built a likelihood function. Your homework is about likelihoods, maximum likelihood. All the purpose of that is to give you the mental constructs, mental representations of what's happening, how it works, because then once you get into your actual practice with this, you'll know what to look for with respect to what's in the likelihood, what's not in the likelihood. How do I know that I'm actually doing things that meet the assumptions of missing at random? So those are the things I'm getting into. All right? All right. Anybody have thoughts or questions about that? Gosh, it's quiet in here. Anybody got a good joke? I'm going to break it. I'm going to break your spirit. You're going to be happy by the end of this class. I'm telling you. Maybe probably it's happy that it's over. Okay, maybe not. Never mind. No jokes, I promise. No singing in this class. There's no jokes. I'm sorry, there are jokes, bad ones, but no singing. That's Lisa. That's not me. All right? You're laughing. You know what I'm talking about, right? She sings in your classes? Wrong guy. Wrong guy. All right, let's get into this lecture. Actually, let's stop. Let's not get in yet. What happened last week? Remember what we did? We had 2 weeks ago we had distributions and types of distributions, joint, conditional, marginal, right? And again, this is like this is the stuff you take in mathematical statistics, but I want to give it to you here because you're going to have to work with each of these, even though, like it doesn't seem like you are, right? So for instance, can one of you give me an example of a conditional distribution that might be implied by a model? A normal distribution. Normal might be marginal though. How would you, actually, let's put it this way. Give me a model that implies a conditional distribution. Let's try that. It'd be a very simple model. Exactly. When we regress y on x. So if we went about and created y for a person equals beta 0 plus beta 1, x for a person plus error for a person, this implies a distribution. You remember what that distribution is? Right? We would say y for a person given x for a person follows, right? And I'm guessing when we regress, you're going to say that we have to say that error has to follow a distribution, right? Right there, right? So when we do that, this is now a conditional distribution where the mean of it is beta 0 plus beta 1 x, and the variance is the variance sigma squared e from E. So this is an example of a conditional distribution, right? Before that, when you learned regression, did you know it as a conditional distribution? No. And that's the link I'm trying to provide here, right? Tying things that you do know to these MathStat terms where the general idea of missing data runs on in a way that sort of brings you along with it. We're never going to prove anything. We're never going to do like the theoretical statistics. I'm not the guy to teach you that, but I am trying to teach you how to like decipher what they're doing and why they're doing it that way. But yes, this is an example of a conditional distribution. You could think about a PDF for our normal distribution density, right? And you could think about, well, that's it, right? So yes, there's it. Okay, but so that was 2 weeks ago. Last week was talking about now how do we go and turn a distribution into a likelihood function, right? And that's where we, excuse me, that is where we took, if we say that the distribution of yp given x is that normal PDF, right? The sample likelihood would be the product from person equals 1 to capital N people, that distribution function, right? That is not often what we work with. What is often what we work with is, this is, if we take the log of it, right? This then becomes the sum across people of the log of that distribution function. Right there, right? So that's our progression. But one of the things that we've realized last week, one of the things I didn't realize, but the scope that we taught it in, I taught it in, you listened to it in, was that in this distribution, it looks like there's two variables, but really there's only one, right? X is stated to exist with no assumptions. Sometimes we call it fixed. It's just there. X doesn't, we need X to clearly create this example, but what we're saying is given X, that's literally what the definition of a conditional distribution. Conditional on X, given that it exists, here's what we think Y will do, right? How many, then, if you were to look at this likelihood function, how many random variables is it describing? It's a little bit harder topic to ask, but that's, excuse me with my terrible drawings here. Oh, I need the object eraser. Come on. There we go. So in this distribution, how many random variables are in? Just one, right? It's Y, right? How'd you get to one? Mean value. I would say this. I get to one by saying what's fixed and what's not fixed. Again, right? So here, do I have a laser pointer? I may do, but that's all right. Well, we know we didn't say anything about beta 0. So when we don't say anything about it, we don't assume it has a distribution. So it's just a constant. Beta 1, it's a constant. X, oh, that's a constant, right? Now E, that thing's random, right? However, it's in the equation that leads to Y, right here. So now what we see is Y is made up of a bunch of constants and that random thing, so therefore Y would be random also, and that's our one random variable, right? We would call this a univariate conditional distribution, meaning we use the standard univariate normal density function in our likelihood. And do you remember the univariate normal density? Do you want me to remind you what it is? I got it right here. We use it all the time. Here, I'm going to do it anyway, just because of, just because. All right. F of y given x equals 1 over the square root of 2 pi sigma squared times e raised to negative, in this case, y minus the mean of y, squared, this is not all over 2 sigma squared. How to do with that? Anybody want to check my work? Sorry. You get this when you start working with distribution, it gets like normal gets drilled into your brain. It's just going to be there, right? But again, looking at this, right? Y bar, that's our, keep doing it. That's our mean right here. Those are all constants that we saw before. Sigma squared, we said that was a constant. We didn't give it a distribution, right? So the only thing that's random in this distribution is y itself. So again, I'm making a big point of that because when you get into multiple variables, like the structural equation modeling format that's talked about at the end of chapter 3, you no longer have one thing that's random. It's now a multivariate density. And it's interesting because a multivariate density has some features that work with missing data that you won't see with the univariate density, right? So for instance, if y is missing, what do we do with our density here? What can we do with the observation? Nothing. We don't have a y, we don't have anything to evaluate it with, right? So someone who doesn't give us y, we're stuck. Similarly, what happens if x is missing? Now again, it's not on my screen here. If I go up here, if x is missing, how do we give a person a conditional mean? Ugh, can't do anything with that either. So in a multivariate density, which is the thing that we're going to start with today, and we're going to get into multivariate normal because it sort of fits with a lot of the structural equation modeling framework, which you can tell this person who wrote Enders wrote it is sort of trained in SEM. If you're trained in SEM, everything's SEM. If you're trained in not in SEM, you're like, why is everything SEM? So depending on your training, you may feel that way. I'm going to be somewhat agnostic. I'll use his words since we're reading his book. In the SEM framework, multivariate normal is our density. So our likelihood function now has multiple things that are random. And in that case, the things that, if you have missing data, so long as not all the random parts are missing, you have just one piece of data, you can resize the multivariate normal into a smaller normal distribution based on its properties and continue on. And that is the key to thinking about why maximal likelihood works with missing data, in that you're not throwing away all the data, it's that you're retaining the cases, the observations of the cases that you do have, and you're adapting your distribution to fit those rather than just omitting them altogether. Does that sound okay? Okay, did that come at all come through the chapter? Okay, I hope so. So that's today. All right. So, but, and here's the teacher in me, right? I don't know how many of you played with multivariate normal distributions, and I'm not going to make that assumption. I didn't make that a prerequisite for this class. So today we're going to talk about multivariate normal. And if you already know multivariate normal, this will be familiar to you. If you don't know multivariate normal, please ask questions. If you have questions or concerns, I would absolutely welcome the chance to try to resolve those for you. And I will tell you, you won't be the only one with questions. Okay? And again, try to say it. I respect all your questions. Everyone. I try to make you feel respected if you ask a question and not humiliated, because I felt that way before when I asked questions in grad school and I reject that. All right? All right, so we're going to talk about multivariate normal distribution. We are not getting through all the slides. There's 100 and some odd, and they're terrible at the end. And so what I'm going to end up doing is I'm going to get through where I can get through today. And then the next time we have lecture, which will be 2 weeks from today, I will have a better idea, a better organization for what the end matter looks like. And we'll cover how the SEM framework works with the factorized regression, why you'd pick one, maybe even try to put a flow chart together of figuring out when you'd pick one versus the other. Because I felt like, to me, trying to put myself in the reader's shoes that hasn't had the experience I have, it feels like it doesn't seem clear from what's written yet. Okay? Okay. So multivariate normal, the rest we'll get through there. Here's our data example. Still using the IQ and performance data from his last version, just because I like it. Seems reasonable. And it's simple to begin with 20 observations and 2 variables. The thing about multivariate distributions and multivariate statistics is that you quickly lose the ability to visualize what's happening. And I think I'm more of a visual learner. once I understand the visual, I can go and then try to recreate it with mathematics, and I can, play around with symbolic notation and see how plots change. Oh, that's how it works. Multivariate distributions don't work that way, right? We're lucky if we can plot in 3 dimensions. And 4, it's got to be moving, right? That's, forget it. So we quickly run out of space to do this. But again, we have 20 observations. We have IQ and job performance, and we wanted to say that the idea was that a person's job performance was somehow related to their IQ. And again, I'm mentioning that we have a few descriptive statistics here. We have the means. I'm going to reorganize those means to something called a mean vector, because now you're going to hear the terminology that shows up with multivariate normal, because there are cases when you're reading about it that people will call that a mean vector, right? We'll also talk about the covariance matrix, right? I mentioned before, covariance is tough to work with. We much prefer correlation because it has it's unitless, right? It's bounded between -1 and 1 in multivariate continuous data. But covariance is the matrix that shows up in the distribution function, the PDF of multivariate normal. So we have to be familiar with covariance. And once we get to covariance, all sorts of things get crazy because we have to make sure that covariance matrix cooperates. By cooperates, I mean has some features that allow it to be inverted. And what inverted means, I will talk about in just a bit as well too. Okay, questions? That was a slide trick to let you know I'm about to cough, so I'm gonna drink some water. Oh, all right. So up to this point, we've just worked on a single variable. That was the whole preamble of what I'm talking about today. Even one variable, we sometimes call that univariate, right? And as you saw, there's 2 weeks ago, we talked about 2 types of univariate distributions. There's marginal, right, which is just one variable by itself, right? Not a conditional mean, just the mean, right? Think of it that way. And then there's a conditional distribution. We just saw just a moment ago that conditional distributions can also be univariate, right? So for right now, it's okay to think about, well, up till that point, it was okay to think about that. What I'm going to tell you now is that conditional distributions can be multivariate, right? So let's imagine a situation where that would be the case. Later on the slides, I'm going to have a different example where we're predicting, we have basically 2 regressions. We're looking at perceived usefulness of mathematics. There were some other, and mathematics performance. So think about math anxiety, studying math anxiety or something along those lines. And somehow we get a measure of math performance. We give a bunch of students a test. We have a measure of math anxiety. We give them some type of scale. Those are our outcomes. And we're both going to predict that based on certain features of the people. Maybe their biological sex, male, female. Maybe their, if they, how many credit hours they had for like coursework, course credit, right? So you could imagine that's a decent regression, right? If you would take one of those variables by itself, you'd say, hey, math performance should be related to perhaps something to do with gender, although there's nothing about a human's brain that prevents any person from learning math, right? Maybe some learning disabilities, but not gender or sex, I don't think. And then maybe the number of credit hours. So you would expect, hey, there may be an impact of credit hours on performance, right? Something like that. And then perceived usefulness of mathematics, same thing. Someone's sex, and predict it with someone's sex, predict it with someone's credit hours they've taken in math classes. Now we have 2 linear regressions, right? And I think at the last week, I tried to show you how you could sort of try to trick LM into doing 2 or GLM or, into doing 2. But that is our entry point into what Enders is talking about as the structural equation modeling approach, in that we can actually estimate both of them simultaneously, right? Sometimes we call it simultaneous equations. That's an older term, or used in other places. I think econometrics, someone calls it that. But then I would call this path analysis. It's a very basic path analysis, but we have 2 regressions for it. And so in that case, the conditional distribution now has 2 y's, right? One for performance and one for usefulness. And they're both conditional on the two x's. So that is an example of a multivariate conditional distribution. Right? So where we described it before as univariate or not, now we're getting into a place where most of our distributions will be multivariate conditional. And then later on, we're going to find out that if we stop the belief that if we add to this simple equation, I said, oh, x is fixed. But if we said, no, actually, x isn't fixed, x follows a normal distribution with some mean of x and some variance of x. Now we can put all the variables in the likelihood function. And now we have another use case for multivariate likelihood function. Okay? Yeah. How's the pace? Is it okay? All right. So we need to know a little bit about joint distributions. That's where this comes from, right? Last time, we're building up slowly, stair-stepping here. And the path analysis or structural equation modeling software that I'm going to use is the Lavaan package in R. Lavaan was sort of a mirror of what started as sort of a open source version of what M+ tries to do. M+ being proprietary, somewhat expensive. Good software, but I'd rather give you the open source and think about the concept from it as we go further. So path analysis, not just path, but path analysis is what Lavaan does. And path analysis, and what we're going to use with it in this lecture, is how to explore joint distributions, right? See what their parameters should be, figure out how that contributes to the likelihood function, and sort of understand what we can get out of it in relationship to other different distributions. When I think the very first lecture of the class, I started with the Lavaan, and I said, oh, I took this regression and I just changed things around a little bit and I put it into Lavaan. I might get you there as well too. That might come next week. So now that means we're just going to have to adapt our conditional distributions to have multiple variables simultaneously. I'm going to put laser color here. And laser pointer. There we go. Right here. So what we're going to do right now is look at the joint distributions of two variables. Not one, but just two. Started with two. In matrix form. A lot of times these, if you got down to the end of the chapter, did you see some matrices in the equations? How many of you went like, yeah, symbols, oh my gosh, right? Yeah, I got there. Some of the path analysis matrices, like the equations for it are like ridiculous. Like, so I'm going to Germany next week, and I'm trying to learn German a little bit, right? It's a complex language in some ways, but how they compound words, and you can get like very long words without spaces because you can add adjectives to nouns. That's what learning about the matrices and the path models did to me. It was like, oh my God, like, right? So I'm going to try to unpack some of that. I'm going to talk a little bit about matrices as well too, because a lot of times if you're trying to do this on your own, what I'm hoping to do is give you some background information that you can rely upon on why it looks that way and sort of how to parse what's being written about. All right. Okay. So I'm going to start by saying f of x1 and x2. That's a general math term for a function of two variables, right? Sometimes we call that a multivariable function, right? If I put x1 and x2 into this matrix, capital X, the matrix itself has, if we were to put our data frame there, we would have n people in the matrix and two columns, right? One for x1, one for x2. So therefore, my notation gets a little simpler. I will say that matrices, once you start to understand them, makes notation a lot easier. And that's why you see it everywhere. In fact, one of my advisors, one of the professors I learned a lot from in grad school, Rod McDonald, used to sort of hypothesize that, factor analytic methods were sort of hamstrung by the lack of having matrix algebra back in the 1930s. And as soon as matrix algebra became more readily available and understood, that really accelerated the pace of quantitative research on the methods themselves. So you may hate the matrices, but the reality is they sort of shorten a bunch of equations to make it a little bit easier to read once you understand them. but that's a huge leap, right? You have to go and learn them to understand them. So we're going to begin with two variables. Remember, last time when we have a PDF, we started with the idea you plug in X, you get a height. We're going to start with that same idea, but now to work with a multivariate distribution, we can't just plug in X1. We have to plug in X1 and X2. So what this is going to return to us is a single number, that same relative likelihood we called it. But it's now the relative likelihood of observing X1 and X2, not X1 or X by itself. Right? And actually, you can even think about that. When you see the comma here, or when you see a matrix X, a function of, you just say and, put and there. These are all the variables all at once. Here's how likely it is to observe all of those, not just a single one. Right? All right, so we're going to start with looking at multivariate descriptive statistics. Fun times. Mean vectors and covariance matrices. All right, how are we doing? Okay. So one thing we have is two variables. I showed you the mean before. X was 100. X1, IQ was 100, that's X1. And then performance is 10.35, that's the complete data version of performance. And if we were to put that into a vector, first, we would have, let's just start with X. In this notation, I described the matrix X. Now, when I write matrices with symbols, I put a half arrow over the top. I learned that way a long time ago because I can't boldface the matrices, right? In symbolic, when I write a paper and there's matrices in it, a matrix is usually capitalized and boldface, right? So capital bold X for a matrix. That's what this is right here. That X should be capital. It's hard to tell with just X up there. And the little half arrow means it's bold. That's a matrix, right? So this is just a box of data, right? Where we would have X1 for the first person, X2 for the first person, right? And we'd have X1 for the second person, X2 for the second person, and we'd have all those X's down to X1 for the nth person and X2 for the nth person. So that's our matrix of data, all right? Turns out if we want to play a trick with matrices here, we could actually create a matrix of ones, sometimes a vector of ones. A matrix is a box of data that has more than one dimension. A vector is often called a matrix where one of the dimensions is equal to 1, right? So a row vector would be one of the rows of a matrix. A column vector would be one of the columns of the matrix. So here I'm going to create a ones vector, and it's going to be pretty stupid. One of the things about matrix algebra is you learn a lot of tricks to do the math that you want to do. So a lot of the math that you know, like summing up problems, is like using matrix multiplication plus a bunch of ones and you get a sum. All this is the number 1 repeated capital N times, right? So if we wanted the mean vector, right, we could just take the mean of each variable, put that in a little matrix and call it good, but there actually is a matrix calculation for it. Here we take the scalar 1 over n, and we take our X matrix, this T means it's transpose, and we multiply it by a vector of ones. In this case, this ones matrix is n by 1. So I'm not going to get a lot into matrix multiplication. I'll tell you this real quick. I should usually have slides for it. But in matrix multiplication, a quick primer on that is if I have a matrix A, which is A, B, C, D, and a matrix B here, which is E and F, right? Matrix multiplication only works when matrices conform to the right size. You may have seen errors in R before. It says something about non-conforming matrices. And you're like, yeah, I like non-conformists. Let's not all just conform. But that just means they can't get multiplied together, okay? So what you do for a matrix multiplication is this matrix A we'd say is size 2 by 2, and B here would be 2 by 1. The first number there is the number of rows we have. The second number is the number of columns we have, right? So far, so good. So to do matrix multiplication, it matters which matrix comes first in the notation and which matrix comes second. So if I took the product A times B, if I was looking to create a new matrix C, and I should make my notation consistent here, right? What I would have to note is A is sometimes called the pre-multiplying matrix, and B is called the post-multiplying matrix. And what you need to have is the number of columns of the pre-multiple have to be equal to the number of rows of the post-multiple. If you don't have that, and you're trying to do this in R, that's where you get the error non-conforming matrices. Okay? So first things first, these two match. So I can create the product A times B. If you're thinking like, what, you can't multiply some things? That's weird. I don't know how to do that with scalars. Totally understand. There's always something like that that comes up, but for now, let's just pretend our boxes are the right shape. A lot of what you see with the matrix notation you get is people overcoming things like, oh yeah, I can't do this multiplication. I'm going to rearrange my numbers a little bit and do it this way, so the symbols change. But so we have pre-multiplying A, post-multiplying B. It turns out the new matrix that you form, this new matrix, has the number of rows of the pre-multiplier, so there'll be 2 rows, and has the number of columns of the post-multiplier, so 2 columns. And the way that it works out is that we can then go form each of the cells by taking element-wise products, sometimes we call those dot products, of the varying row and column vectors. So if we want the entry for cell 1, 1, we take the first row of the pre-multiplier, take the first column of the post-multiplier, and actually, I've already gotten this wrong. This should be a 1 right here. It takes... God, I'm rusty at this. The size of this thing, let me back up. Oh. The size of this thing is the number of rows of the pre-multiplier and the number of columns of the post-multiplier. You know that I'm going to screw this up without my slides, right? Need slides for this. But here we go. So this is a 2 by 1 that we're going to get out of this, right? So again, though, we take the first row of the pre-multiplier, multiply it element by the first column. So what does that mean, element by element? This would look like this. A times E, and then B times F. Those are the corresponding elements. A is in the... What the heck just happened there? A is in the first position. B is in the... E is in the second position, right? Sorry. A, E, B, F. And then we add them together. So this ends up being AE plus BF. So that second one will get CE plus DF, right? CE plus DF. And there's our result. That's matrix multiplication. Sorry for quick primer. I struggled with whether I wanted to include it. But now we can talk about X for a little bit here, right? And X, our X matrix, would be the pre-multiple here. And 1 would be the post-multiple. We know X is size n by 2, but its transpose takes the matrix of this long matrix of n by 2 and transposes its rows and columns, makes it very wide. So the size of that is now 2 by n. All right, so X transpose size is 2 by n. The size of 1 is n by 1. So we can multiply them together because the number of columns of X transpose, n, is equal to the number of rows of 1, n. The resulting matrix then will be a 2 by 1 matrix, which is this down here. And when you do the products for the math, you think about it, here, if I flip over, if we took X transpose times 1, each one of those products, right, we have to take every element of the first row of X multiply it by every element of the first column of 1. And since 1s everywhere are there, what that results in is just x values summed together to give us the sum of x. Right? So this is the trick. This is matrix multiplication for the sum of x, is what this is telling us. But because we have more than one x in our matrix, we get all the means taken care of. Pretty cool, right? I think. I don't know. Do that in R instead of apply. Something like that. Questions on any of this? All right, so there's our mean vector. We good? The mean vector is the standard distribution of all the variables. We remember that as well. Here's IQ, here's performance. There's our regression line. It's on the regression line. Let's talk about the covariance between the variables. The covariance is a measure of how related the variables are, how much they co-vary or vary together. Right? And this term, if you're familiar with the correlation, this looks a lot like what goes into a correlation formula if you're taught basic statistics or taken basic statistics recently. So here, the covariance is the sum of n, sorry, 1 over n times the sum of the first variable minus its mean times the second variable minus its mean, right, for each person. Right, so we don't use covariance a whole lot. Here, technically covariance has units attached to it. So we would actually, the scale of it is in IQ units times performance units, IQ perfs. Kind of like in certain types of physical measures. Like I think of, maybe because I like, like cars, a measure of how much power a car has is the torque it may have, the engine may have. That engine torque is in foot-pounds, right? I don't know if you've heard that before. I think that's what it was. Pound feet, pound feet. Is that right? Anybody with torque experts? No. Someone's nodding. Yeah, does that sound right? Maybe not outside the United States, since but it's hard to do that, right? So here, n is our maximum likelihood version. Typically would be n minus 1 for what we would call sample and basic statistics. So n again shows up like we saw last week. N was the denominator when we saw the standard or the variance formula for ML. So because of those units, IQ perfs, 20.3, I can't tell you if that's big or little without knowing more information. It's often why we then convert covariance to correlation. Correlation is the covariance divided by the product of each variable standard deviation, right? That right there. So if S was in IQ units and performance units, and the standard deviation is IQ units right here and performance units there, we've sort of removed the units from the equation, and now correlation ranges between -1 and 1. But you've seen that before. And here you have it. Turns out there is a matrix equation for this. Wouldn't you like to know? Here, nope, that's it. My R code. You can, of course, grab the covariance from your data, right? Right here. If you took the diagonal of the covariance from your data, then it turns out whenever you see the solve function in R, that's like doing the dividing by, it's a matrix inverse. It's not exactly division. I do need to find this, and I don't think it's in my slides. A matrix inverse is such that if you have A times its inverse, which is usually denoted as the matrix raised to a -1, right here, this equals something called the identity matrix. The identity matrix is simply a diagonal of 1s, and the off diagonals are 0s, right? So that's a definition of matrix inverse. I think technically the definition works in both ways. Because pre and post multiple work the same thing works. It's just this may be the case. So we're talking about correlation and covariance. D is a diagonal matrix, only has numbers down the diagonal. When we take the inverse of the diagonal, it's like taking 1 over each of the terms in it, right? And so what happens is we take S, in this example, and again, I'm doing this just to elaborate matrices for a second. My S matrix looks like this. It's sigma squared x1, sigma squared x2, sigma x1, x2, sigma x1, x2, right? That is my covariance matrix. My diagonal matrix then would look like this: sigma squared x1, sigma squared x2, and zeros, right? Then my inverse of the diagonal matrix, and this is true for diagonals, but not true for non-diagonal matrices, it's 1 over sigma squared x1, 1 over sigma squared x2, and zeros otherwise. And so now you can see how we're building a matrix result to give us a correlation matrix from covariance. If we take the correlation matrix here is the diagonal matrix times the covariance matrix times the diagonal matrix, right there, right? So if we do our matrix products, first of all, I always check the size. Diagonal matrix has 2 columns, S has 2 rows that can multiply. So if we do the first multiplication, we get the following. We have to take the first row of this, so we get this row times this column. And you note conveniently that 0 is knocks out our covariance there. So this will be sigma squared x over sigma squared x1, right? And, oh, of course I screwed this up. The diagonal matrix is the diagonal matrix of standard deviations. That is my problem. So let me go back. Of course. Jonathan, come on. Sorry, folks. Disgusted here. All right. D, the diagonal is standard deviation. Get nervous when I make mistakes. You ever have that happen? I've been teaching like my first class I TA'd, I got to TA as an undergrad like 1997. I mean, like 30 years ago, and I'm still this way. So my bad, right? So diagonal square root. There we go. When we do that, work the math through. This is sigma squared x divided by, oh, come on, sigma x. And then basically, in the next spot, we have sigma x1 x2 divided by sigma x1, and then so on and so forth. I'll just leave it there. Bottom line is you get your correlation matrix back. All right. Yes.
Is that related to the concept of information? Because 1 over variance or something is information, right? Or is that different?
In our case, it's a bit different. If you think about what you learned about Fisher information, 1 over -1, or basically the inverse of -1 times the Hessian matrix, gives you your matrix of standard errors. But this is what I was trying to show here. This part is not related necessarily to it. This is just matrix calculation on going from covariance to correlation and backwards. Right. A couple other notes that I'll put, then we'll go to break. There are other features that we need. Right. Turns out the multivariate normal distribution depends on the mean vector and the covariance matrix. Those are the 2 sets of parameters that it depends on. That's where I introduced those. The other things we'll talk about is something called the determinant. The determinant of a matrix sort of quantifies, it's a physical definition. I don't even know how to tell. I'm going to drop the physics. I'm just going to give you the blunt definition. It tells you whether or not you can invert the matrix, right? There's a physical property to it. You can talk about area under a hypercube, but then you have to imagine the vectors are this n-dimensional vectors into a hyperspace, and let's not do that, right? Determinant of the matrix, determinant function, hard to calculate, but if it is greater than 0, the matrix inverse exists. Technically speaking, our multivariate normal needs the determinant to be positive semi-definite, which is 0 or bigger itself. And if you take a multivariate statistics class, you'll learn that the determinant of your covariance matrix is also called your generalized variance. Basically talking about how long the vector of data happen to be and how correlated they are. So if you were to think of, I've got x1, it's a vector going off into 500 dimensional space this way, and I got x2 going that way, the angle between them talk about how correlated they are. The angle gets smaller, they're highly correlated. The angle gets wider, they're not correlated. And what this is calculating is the area of the cube in that weird space. So the bigger the generalized sample variance, is like having a variance of multiple variables altogether. But it's factoring in how related they happen to be. Right? Similarly, if the trace of a matrix is much easier to calculate. I'm not even giving you the formula for the determinant, but for the trace, you sum up the diagonals of the matrix. We call that the total sample variance. It's often used when we look at variance accounted for measures, often in like exploratory factor analysis and so forth. All right, I'm going to pause there. Let's take 10 minutes, come back a little bit after 1:30, and we will resume the torture that is me trying to struggle over which formula needs to be right or versus not. I'll do better. All right, thank you. We'll keep recording. All right, any questions for me about what we covered to this point so far? Okay. So now let's talk about the multivariate distributions when we have more than two variables. The multivariate normal distribution takes the univariate normal distribution and generalizes it so that it has more variables, more things that are random in it. Okay. The multivariate normal distribution, we got an f of x here. We give it a vector of a person's data, right? It's not capital X, we just take a person's data, right? Remember the univariate normal is specified for each person to begin with, and then we went from each person to the sample, right? So let's start with a person here. So a person's data, this is like a row of that X matrix, right? So you may have capital V variables on a person. What the multivariate normal distribution will tell you is how likely observing that profile of variables would be for a person, right? Before we used to say, hey, here's a person's height, like univariate normal. I'm 185 centimeters, 6'1", somewhere around there, right? You could go and plug me into a distribution of dude's heights, my age. You should get back a relative frequency, right? Probably put me on, and if you were to go turn that into a, cumulative distribution, I'd be 85th percentile, but on the curve, I'm toward the higher end, but certainly not super tall, right? So with two variables now, you're going to be like, okay, that's his height. Let's give me his weight. Now, how likely is it to observe somebody who's my height and my weight is what you're talking about, right? So it adds more features. But again, what comes out is just one relative frequency, which can be any number, right? Any number above 0. It cannot be negative. Any number above 0, right? So even though a lot of times these numbers are between 0 and 1, remember, it doesn't have to be that way. So let's talk about this distribution itself. Tell me on a elegant looking scale, like, doesn't this look elegant or ugly? What do you think? How many of you say this is an elegant looking function? I think it's beautiful, personally. How many think it's ugly and intimidating? Or just ugly? Anybody have ugly? Ugly. How about intimidating? No one wants to admit that. I won't ask that. It's okay. You're not intimidated by math on page. It's just math. You will get there. All right. But let's take it a little bit further. In the front, you've got 1 over 2 pi. Now remember that normal distribution, univariate normal, had 2 pi in it before. So there's your clue. 2 pi is there. 2 pi is raised to the number of variables over 2. Okay? That multiplies, you see those lines by sigma? Sigma is your covariance matrix. Putting that in lines like that indicates you take its determinant. Right? And you can immediately see why we need this determinant to be 0 or bigger, because this thing is a constant. 2 pi will always be positive. And if the determinant becomes negative, our relative likelihood goes negative, which can't be. Right? So sigma, put in bars, is the determinant of sigma raised to the 1/2 power, or the square root of the determinant of sigma. How we doing? Awesome. Then we have the exponent again. And now we get the idea of matrices getting projected onto things that you know, right? When I mentioned before, matrix multiplication sort of looks weird sometimes because we sort of trick knowing how matrix products are formed and build our matrices so that they will work out to give us what we need. This is an example of that. In the univariate normal equation, we had x minus its mean squared, right? Here we have x minus x transpose, right? Remember, x is 1 by v. The mean vector is v by 1. And turns out when you add or subtract matrices, they have to have exactly the same number of rows and columns. So 1 by v transposed is size v by 1, which fits just fine. So v by 1 goes in here, and that whole thing gets transposed, making it 1 by v. 1 by the number of variables. The covariance matrix, that is its inverse. -1 is a matrix inverse. And it needs to be of size number of variables by number of variables, right? We know that about a covariance matrix. We know about correlation matrix, right? We know the size of it. So if this thing right here is 1 by v, we already know it multiplies a v by v matrix. And that first part of this turns into be a 1 by v size result. Well, this other term over here is a copy of the first, right? And that copy of the first is size v by 1, right? Because this thing is 1 by v transpose, or v by 1. This thing's v by 1. So what we end up getting is a 1 by v thing right here. This is 1 by v times a v by 1, which results in a 1 by 1 matrix. And every time you have a 1 by 1 matrix, we can call that a scalar. A scalar is just a number. What you knew. So you immediately see that even though you put matrices in, nothing is going to be a matrix coming out. A determinant is a single number. All these other things are scalars. We get a scalar out of it. We get a single number. So that's the engineering nuts and bolts of how the whole system works. Oh, here's your mean vector. Probably should have said that first. Covariance matrix. Right? And if you wanted to generalize it, right? This is our univariate normal. Here's how we could have rewritten it to make you see it was already getting you ready for multivariate normal, right? So if I take the idea that 1 over sigma squared is really could be written as sigma squared to the 1/2 power, right? I could do that. So I can move sigma squared right up here, right? And sometimes in scalar, like when you learned, well, maybe I have a false memory, but when I was younger, I learned if you have a letter A, like in algebra, 1 over A is its inverse, right? Remember that? Like just like a single number A, right? Because A times 1 over A gives you 1, right? So that's sigma squared's inverse right there, right? And then if we took x minus mu squared, we really could put it on either side with some algebra and get that there. With x minus mu times sigma to the -1/2 power times x minus mu. And that rearranges our equation to look a lot like how it works with matrices. Similarly, right, in the what we call the normalizing constant, if we look at anything under the radical, that's like calling it to the 1/2 power, right? So 2 pi to the 1/2 power looks like this. And I think this should be sigma squared, this sigma to the -2. Screwed that one up. Yeah, sigma squared negative, yeah, sigma squared, yeah, sigma -2 would also do the same. Sorry about my typo. Then here, sigma squared, turns out the determinant of a scalar is just the scalar. Sort of a dumb idea, definitional idea. I say dumb a lot, but really what I mean is that's defined that way. There's no elegant thought put into it, at least not by me. again, it's under the radical, so it's 1/2 power as well too, and that sort of maps on here. So if you think about a univariate normal, there's one variable, so this v is a 1, but everything else is an extension. Again, this term right here, my math was off. This should just be, there we go, right? Like that. So what I'm getting at is each of the components that's in the generalization of the multivariate normal started with the univariate normal already. So it's functioning in the same way. How's that work for you? Cool. Here's some multivariate. Now I'm going to give you some multivariate normal trivia. Not that you wanted it, but just when you're at your parties with your friends and you want to impress people, this is it right here. All right? The term in the exponent is sometimes called the squared, and I kid you not, we call this the Mahalanobis distance. I believe named for the person who probably talked about it or showed how it was distributed. It turns out this thing is like a multivariable z-score, but it's a chi-square distribution. Sometimes people have used that to assess if data are jointly multivariate normal, right? You can think about QQ plots of chi-squares versus squared Mahalanobis distances. But I personally love the word Mahalanobis. So if any of you want to name a band, a human, maybe not. I tried to get Lisa to let me name Hugh Mahalanobis Hofflin. What do you think? Would that have gone well? Probably not. She shot that one down. Okay, well, how about Hugh? And that is what I learned in social psych as the door in the face technique. Of course you can't do that. Well, here's Hugh. Oh, that sounds reasonable. Fine. All right. Not a true story, I promise. But you can envision it. Darren Hugh. Great name. Anyway, so how we refer to the multivariate normal in notation, usually capital N and the number of variables below. Oftentimes the number of variables go away when you see matrices in bold in the parentheses, mainly because it's assumed in there. So in our data example, we only have 2 variables, so it'd be N2, and often that gets referred to as a bivariate normal distribution. And the bivariate normal distribution you may have seen before because you can write the bivariate normal distribution without matrices if you want. I'm going to see if I can quickly grab it. It looks like that. But a lot of people, yeah. Would you rather have this or that right there? I like the matrices, right? If it's for 1, if it's for 2, if it's for all. The point I'm trying to make, though, actually I should have said this in this slide, is that I did say it. If your variables are 1, this thing becomes univariate normal, right? That's the other point I need to make there. See where I'm going with this? This missing data, if we have 2 variables, some people have 2, some people only have 1. Can we use it? Absolutely. We can use both. So that's the key about missing data. That's the tie to what we're doing, okay? Okay. So in multivariate normal, this distribution itself is literally the basis for almost everything that you do with continuous or plausibly continuous data. General linear models, ANOVA, and if you generalize ANOVA or regression to multiple outcomes, we used to call that multivariate analysis of variance. More recent iterations, recent being 50 years old, talk about mixed models, right? And there's equivalencies between what you know, what you may have learned as MANOVA in the old school sense, and mixed models for MANOVA. Those rely on multivariate normal distributions. In fact, one of my favorite packages, Proc Mixed in SAS. I love their user guide. I think I learned about mixed models more from it than I did anywhere else in my life. But I was just going to get down to, they describe their likelihood function. And I'm not going to show you REML, but this thing, ML right here, that actually is the log likelihood of what we're doing. R is y minus its mean. V is your covariance matrix. And this is the log of all of it. Right? So it's literally right there in mixed models as well, too. You can use this for factor analysis, confirmatory factor analysis, which we usually assume factors are normal, errors are normal. Exploratory factor analysis, path models. My definition of structural equation modeling is path models with latent variables. Sure enough, it shows up there too. So long as all of the observed data that you're talking about follow or assume to follow a normal distribution, multivariate normal shows up there. And sure enough, multiple imputation shows up there. So simply put, everything that you probably have taken a class about is sections of using the multivariate normal without even knowing about it. Right? So to me, why we're talking about it, again, is the high level. Right? We need to understand that we're using all the data we can in the likelihood. And since so many models use multivariate normal, it's a nice way, and actually multivariate normal is easy to see how the likelihood adapts to missing data. We use it here. But to me, it also helps you understand the process overall, right, of how likelihoods work and how likelihoods work for missing data, and then hopefully how likelihoods would work for missing data in a context that would be much more familiar to you. All right, questions? Okay. How about we look at a plot? Of course, my notation is not hidden here, but this is plotting the multivariate normal distribution. All right, so let's imagine this is x1 right here on this axis. This is x2 on that other axis. And this is the result of the distribution, the PDF, the relative likelihood. Right? So our mean vector, in this case, is centered at 0. So 0 for x1, 0 for x2. Our covariance matrix is something we call an identity matrix. Right? 1's down the diagonal, 0 is offwise. Why 0? Why am I starting there? Because I got to start somewhere, and putting a 0 there is a very nice graph. Right? So this is the surface. We call this a surface plot, right? 3 dimensions. Good luck. That's as far as we get with plots, right? After that, you got to envision what 20 dimensions would look like. I have no idea. Hurts my human brain, okay? If we were to take a helicopter and fly over the top of it, we would get something and look down. The rings that you see in this contour plot are equal likelihood, right? So what we're saying is any observation that has an x1 and an x2 such that it lands right on that ring will have the same likelihood of being observed. Right? Just like in univariate statistics, the most likely observation is centered at the mean. Right? So when you plug in the mean vector, you're right at the peak. That is the highest likelihood. Right? But what you see with these concentric rings, is that when x1 and x2 have a 0 for a covariance, there's a property of the multivariate normal distribution that's very convenient. That's not true about other distributions. But a 0 covariance implies that x1 and x2 are independent, right? So remember what x1 and x2 being independent means. We could say, I'm trying to connect lectures. If x1 and x2 are independent, what are you doing? Hang on here. It's now telling me, hey, improve your handwriting. I'm like, not now. I'm teaching. Actually, never improve my handwriting. But if we had f of x1 and x2, if they're independent, then we can say f of x1 is equal to, or the joint likelihood is equal to the product of the two marginal likelihoods. Right? Remember that from a couple of weeks ago? Okay. So starting with 0 is really nice there. Right? Pretty cool. Okay. Questions on any of this? All right. Now, again, my notation is off. if I change that to 0.5, x1 and x2 are no longer independent. So what I had just showed you here, this no longer holds. But what you end up getting here is, again, the mean is always, a point at the mean vector is always the most likely value to observe. But now you get concentric rings that start to have an ellipse. Now, you may have seen these types of ellipses a little bit differently. Often in multivariate statistics class, if you've taken one of those, we give you data and then we say, hey, draw the ring of certain concentric probability, and that involves doing things to the covariance matrix, like getting its eigenvalues, eigenvectors, blah, 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 blah. We're not doing that here. We're not planning on doing that here. But what I'm trying to think about here is you can almost envision the scatter plot that would fall under those ellipses. And if you take a multivariate statistics class, at least the old-fashioned way of doing it, you would learn how to draw those rings around your data, right? Whereas with us, we're working with a theoretical distribution. But you can see that's what the shape of the scatter plot would roughly look like. Cool? All right. But now this is really part of why we like multivariate normal. Pardon me for just a moment. I really need to land this part. No, just kidding. There are some really good properties of multivariate normal. We use them all the time. And this is why part of these properties are part of why I said, oh, I fit an equivalent model, but I used Lavon the first week of class. Right? It's also related to the factored regression approach as well, too. Okay? So if you have data that are multivariate normally distributed, if this vector of data x is multivariate normal, then these four things are true. Number one, linear combinations of x are also normally distributed. Linear combination, think of the most basic one, sum all the x's together. The result of the sum of x will be a univariate normal distribution, but still normal, and you can show it, right? Number two, number one we use to help us get confidence intervals or standard errors when we want to go and get different regression parameters. So if you fit a dummy-coded variable in regression, right? The intercept represents the mean of the reference group. The coefficient slope represents the difference between that group, the group of ones, and the reference group. But if you wanted the mean for the other group, right, you'd have to add them together. If you wanted the standard error for that, you can get that with a linear combination. And you know it's normally distributed. So the GLHT function in R, if you're using SAS, the estimate statement, the new parameters in M+, and I don't know what Stata is, I'm sorry. But it's in there too. And SPSS has like a test or something like that. All of those use that to go and give you linear combinations and p-values and standard errors for each of the different combinations of parameters you put together. Right? That's an important feature of what we do. And no, you don't have to rerun the model to get those. You can get those straight from your results in every software package. That's how important they are. Number two, all subsets of X are also multivariate normal. Now, I should say subsets of variables of X. Right? So imagine we have 10 variables here. 10 variables are multivariate normally distributed. You say, I don't want 10, I only want 2. Turns out they're also multivariate normally distributed. You just take those 2 variables out, resize the covariance matrix, resize the mean vector. There's your distribution for those 2 variables. That's useful too. That helps us because we can show that is why when I mentioned before, if someone gives you one piece of data, you can use this. When he gives you 2 pieces of data, you can use this. The likelihood's the same. And when we talk about subsets of variables in our context with missing data, that will be, these are the ones we observed. Well, we will still assume the ones we observe follow a multivariate normal distribution that way. It's very helpful, right? I just mentioned the zero covariance between a pair of variables of X implies the variables are independent. That we don't really use too often. It shows up a lot in some theoretical stuff that we do. But in real life, how would you know that a covariance is truly 0? You wouldn't, right? You can't prove a null. So but we do use that mathematically. And then finally, conditional distributions of x are also multivariate normal. So what I mean by that is, if you take x1 and you say, I want the distribution of x1 given a value of x2, right? I want a person's, the distribution of weights given a person's height, right? So for all the men who are my height, what's the distribution of weight? Sorry, weight's really a personal example. Struggle with my weight. So here I am telling you a story that fits well into my life, right? So turns out we just talked about a conditional distribution before with x predicting y. So when I say x1, my weight, conditional on x2, my height, you can envision that saying, hey, that's like saying, I'm going to form a linear regression where I'm going to predict weight by height, right? And it turns out that linear regression is also normally distributed, just like our linear regression is. So this is the combination. This is the feature that allows us to say, oh, we can build a factored regression approach to what we do to take a joint distribution and factor it if it's difficult to work with. That's where that shows up. So multivariate normal, once you see that that's underneath the hood of a statistical package or a program, the computations get easier. Things converge quicker. That doesn't mean they're going to converge for your data. Don't get me wrong. But compared to other distributions, multivariate normal is amazing in many ways. It may just not be appropriate for your data. Never let data get in the way of a good theory, right? Never mind. That's a joke. Always let data get in the way of your good theory. We good? All right. I said proc IML, but I actually changed this. These were slides I built with proc IML, but I actually built this in R. And if you give me a moment, I can show you this real quick. We're going to play with some of these numbers, talk about how it works. And of course, I go to install a plot. There it is. No, it's good. All right, here's our data right here. Ta-da, we're going to use IQ and performance C. We're not getting to missing just yet. You know, one day I might pull it all together. Okay, let's try this again. Can you see my syntax? Is it big enough? Okay, cool. All right, I'll move this over here. Reading our data, got our means, covariance matrix, and so forth. Just keep going here. Okay, so what I wanted to do is teach you how to do this in R. Your next homework will have you do univariate versions of this, but they're somewhat analogous, somewhat. So R has built-in, well, packages have built-in functions, but first we need our mean vector. X bar is our mean vector. We saw that before. S is our covariance matrix. And you'll note I formatted the mean vector to have 2 rows and 1 column, right? And that's important because sometimes these packages to evaluate the likelihood don't work so well. You have to like specify it in the right way. So here, if I look at observation 2, they had an IQ of 84 and a performance of 13. If you wanted to know how likely that was to be the case, we can use the DMV norm function. This is in which package? It is in the MVT norm package. Why I looked that up was because nearly every package will have a version of this. I kid you not, right? And sometimes it's called DMV norm, some of it's called DM norm, right? But they all work very similarly. We give it our data, right? That's our vector of 8413. We compare it to our mean vector, right? So for instance, the first person is lower on IQ than 100, so lower than the average on 1, but higher than the average on the other. When we give it its covariance matrix, and it actually takes an argument whether or not we want it to be the log or not. That'll be helpful in your next homework, by the way. Not with this function, but turns out dnorm has that function ability as well too. Okay, so we run that and we get a value, and it's very small. Remember, I can't tell you whether or not that means this is a very likely point or not likely point. And again, unlike in maximum likelihood, we're back in just data likelihood case. We know the mean, we know the variance. The flip comes when we don't know the mean, we know the variance, but we have the data, right? I can then also just tell it I want the log. There's the log of it, negative 7.75. Negative 7.75. Well, let's compare that with observation 5, who's lower than the mean on both, 87 and 7. So here's observation 5's log likelihood, right? So which case seems a little bit more likely? It's tough on log, right? Because the higher number is more likely, but logs are negative. So you'd say, oh, this is bigger by absolute value. Turns out that's less likely than that number right there, right? So this is more negative, so this number is bigger. So we'd say it's more likely that you would have observed of 87 and 7 than an 84 and 13. And it's probably because being below the mean on one and being above the mean on the other is a weird spot. If you were to visualize the data, there probably aren't a lot of cases over there. Okay. Let's see what the likelihood of the mean would be. Negative 5.29. Right? So that tells us the most likely case itself. Right, so again, concept I'm trying to get you to learn here, you plug in multiple numbers, you get a likelihood back, right? But it's conditional on X bar and S. So what this part of the lecture is discussing is what we discussed 2 weeks ago. I don't know why I have all these open. I want to see that right there. So 2 weeks ago, we said plug in data, get height. That's what we're doing here. 1 week ago, we said, no. Use this as the basis for your likelihood function, right? Plug in parameters, get likelihood of parameters because the data are already constant, right? So the same process could work here. It's just now instead of having a mean and a variance, I have all the means in the mean vector and all the unique parameters in the covariance matrix. Oh, and there's one other feature that's a problem here, is that covariance matrix having to be positive semi-definite makes optimize, like using Optim or Newton's method or something like that, much harder because you can't just pick random values of the covariance and have it be invertible. So there are tricks you have to play to get over that hurdle. But from the conceptual point of view, does this make sense? Multivariate statistics, multivariate likelihoods, plug in multiple variables with matrices of parameters and get the same likelihood back. Work? All right, we did that before. Well, this is me working this out. There's our correlation matrix. Let's talk about missing data and maximum likelihood then. In a basic sense, by basic I mean you don't have auxiliary variables. All you have are your set of variables that you collected, and they're all in your model, right? Let's just call it that way. In our case, the two variables that we collected are performance and IQ. They're both in our model. Depending on how we specify the model, handling, which I hate that word, but getting the model to run with missing at random assumptions, with missing data, is much more straightforward due to the use of that log likelihood function, right? Each subject is contributing a part due to their log likelihood. So if some of the data are missing, then our log likelihood function uses a reduced form of multivariate normal. And I just mentioned that before. If I didn't observe performance, but I have IQ, I can still run the analysis. Now it's a univariate normal, but I'm still keeping IQ present in the data, in the model, in the analysis, right? So that capitalizes on the property that the multivariate normal, that we have subsets of variables of multivariate normal are also multivariate normal. So we're not changing distribution at all. We're just making the likelihood adapt to our missing data. So the total log likelihood is then maximized. And this is where I talk about this. It's kind of like just skipping over the missing data. It's like, oh, you didn't get job performance for that person. That's fine. Give me your IQ. We'll skip that. Skip the job. It's fine. Right? In fact, this is such a naive way of doing it. I can tell you how when I was even more naive than I am now, back when I was in grad school, I was working on a Bayesian algorithm for the psychometric model. The likelihood function effectively was something that looked like independence, x1 f of xv, right, for all our variables. The log of that then would have been like the sum of these things, right? That, well, you know. And my job as our research assistant was, hey, make this program work with missing data. So you know what I did? My log likelihood, if they didn't observe x2, contributed 0 to the log likelihood. Skipped it. No problem. I'll take the sum of the log likelihoods of the variables I had. Well, as I just mentioned where I crossed this out, if we know that things are independent, that is equal to the multivariate normal distribution in the multivariate normal distribution case. And that fits with what we're trying to do in missing data. And that's why I'm like, really? What I did when I was working out at the Moose Lodge in Champaign, Illinois, on cold days like this to try to figure out how to get this thing to run with missing data, that was what we're supposed to do? Okay, right? But it turns out that's actually kind of important, right? So here's the derivation of it. Again, here's your, if I took the log of the PDF, right? Whoops. The log of the PDF is this for a single person, right? Like if that person observed both variables, this would be the input, right? They would have two variables in their data vector. They would have two means, and they would have two variances and a covariance. But if we assume a person only observed IQ, this would get shrunken down. Now I re-expressed the means on this into a way I probably shouldn't have. But this gets shrunken down to be a univariate problem, right? IQ here is just a mean, which ignore the beta 0, beta 1, that's just a mean for x that, and mu IQ. And sigma is just one element. So I can still use this function, right? The math still works out when I have one observation or when I have two, right? It just changes the size. Okay. Questions on any of that? I think that's cool. Also, I'm really surprised that, oh yeah, my little hack to get the program running. Oh yeah, that's what you do? Now, again, that's a very simple approach. What we get into in the later part of the chapter when we get to auxiliary variables, other things, is that we may want to consider that our missing data go beyond just the variables in our analysis and may be related to other things we may have collected that aren't part of this analysis. That's not how this works. It kind of works similarly. All right, so about standard errors, recall that in maximum likelihood, we derive standard errors based on the information matrix. Information matrix, again, another matrix. We have to take the sample likelihood function. By the way, the sample log likelihood function for this, right, this is a single person. And we assume people are independent. The sample log likelihood function is just the sum of this function right here. Right? So the sum is the sample log likelihood function. So the information matrix differentiates the sample log likelihood function with twice with respect to each parameter, right? So the Hessian matrix is not the information matrix. The Hessian matrix is that, right? That's a matrix of partial second derivatives, we call it. Way too much calculus. But really what that's, again, doing is describing the curvature of a surface, right? As a function of where that point might be. So describing how much curve there might be around a maximum, right? The Hessian then, to get to the information matrix, we can then note that going from Hessian to information is -1 times the inverse of -1 times the Hessian becomes information. Yes. And I'm sorry, -1 times the Hessian is information. The inverse of that is your matrix of covariance matrix of your parameters. Square root of the diagonal is your standard error. But with missing data, when you have a score missing, an observation will contribute 0 to any element of it where the missing score is, where the parameters involve that missing score. So for instance, if we have a person that only observed IQ, and we're after, from our model, 2 means, 2 variances, and a covariance, any one of these parameters not involving IQ does not get a contribution from that person's data, right? So we get no contribution to the mean of performance because we never observed that person's data, and we get no contribution to the covariance between IQ and performance. And the book kind of shows this as well. There's a difference. This right here, this latter part, is what we call observed information. And observed information, as we talk about in chapter 3, there's another type of information. It's called expected. Expected is like if everything goes according to theory. Observed is, well, we've got missing data involved, right? So you can imagine we want to use observed information, particularly because observed information will be more accurate when missing data are present. More accurate because observed information preserves the assumptions of missing at random. Whereas if we use expected information, we have to assume missing completely at random. So what does that actually mean? Because we're dealing not with parameters, not with coefficients, but we're dealing with an information matrix. What does that actually mean? Well, think of it this way. If we use ML and we optimize, we figure out which set of parameters find the maximum of our sample likelihood function, our parameters will do the best they can to be unbiased. Now, ML has a bias on the variances and covariances, but not biased because of the missing data. But we don't care as much about the point estimates are only one part of the story that we need. We need covariances. We need the standard error for each point estimate, the variance covariance matrix of those, and that comes from the Hessian. So it's possible if you're in a case where you're using expected information that you would say, I have missing at random protection for where my point estimates are, but all my covariance, my standard errors are likely to be inaccurate, which still isn't good. Because if your point estimate's wrong, it's bad. But if your standard error is wrong, it's also bad because the standard error goes involved, as we saw in the Wald test, in figuring out if your parameters are significantly different from 0. So observed information is important. And I'm sitting here saying, how many of you know whether you're using observed or expected information when you do your practice? Put it that way. Make it sound like yoga. Have you ever sat to yourself and say, oh man, LM's nice, but I only get expected information out. I don't, right? But it adds a layer of complexity to think about when you get to missing data, which is you got to make sure some of your packages or your R packages know how to do this. Number one. Number two, the book at this point goes into some ML examples, and I'll show you an example as we go through in just a moment here. But right about here in the chapter, Enders introduces like an EM algorithm to try to give a set of parameters. And those algorithms are great. I'm going to try to come up with a I couldn't get his to run from his example website, so I recreated it. I think it's running. I think it's appropriate. I'm going to do another one later in class on the factored regression approach. The result of the EM algorithm, if you're writing it yourself, is awesome. You get the parameters. You don't get the Hessian matrix or your covariance matrix of it. So why you'd need to do that yourself is if you're all of a sudden saying, I'm going to build EM. And you're probably thinking to yourself, most of you are saying, how many of you are going to build your own EM? Anybody? I thought that too. And here I am teaching you in class with an EM algorithm. All right, you never know. But that being said, why I'm mentioning that is EM methods for this, you'll need to figure out the formula for expected information if you want that variance covariance matrix, not just the point estimates, right? Remember, in maximum likelihood, our point estimates come first, and then we describe the curvature around where the peak is of that likelihood function. So, from a practical point of view, I can tell you this. How many of you took Lisa's generalized class? Awesome. You had to use a package called VGAM. Do you hate that package? It's okay. I hate that package. I mean, not hate. Like, it's not like if I saw it on the street, I'd be like, you know, bad things. But there's a lot to it, right? Isn't the manual like 300 or 400 pages? Young, Ahmed, I will say our project with the IRT to DCM, I'm using the VGAM package. It uses expected information. Bum, bum, bum. Oh no, that's bad. At least that's what I was told by Lisa. I haven't infinitely confirmed it, right? But turns out. So as we go on, I'm going to show this now. We're going to use ML for our example data. Most of the packages you'll use, particularly under the SCM framework, will give you observed information. That's good. Okay? Yeah.
Could you summarize the implications of using both? The expected versus observed? Because
yeah.
Only one of them, or could you use both?
No, we'd only use one. We'd only use one. So basically, the implication is this. If you have missing data and your package gives you expected information, you cannot assume that the way it's calculated meets the assumptions of missing at random. And so when that happens, you have to say, okay, my estimates of the standard errors may be biased. That's the implication. Right? Your point estimates for your parameters will be achieved under missing at random, but often those aren't the only point for a lot of inferential statistics. Maybe machine learning, we just care about the parameters. We just train the parameters, but for a lot of inference, we need this to be right. Right? Other questions? Yeah. Yeah. Yes.
So how do we compare two persons that one have the complete data and the other? I know that the log likelihood might be unitless, and we can see the height of this person.
Right.
But
we can't.
Yeah.
I would say this. The only way we could compare is to look at, like, take the person whose IQ here. This is the marginal distribution of IQ. We know it's normal. So if we took the first person and only looked at their IQ, that's the only way we could compare them, right? We couldn't say this person is more likely than that person because the likelihood's now formed on different sizes of components. But the fact that they're all normal, multivariate normal, allows us to have that be the case in missing data. And it just turns out that that allows us for missing at random protection. But we often don't compare two observations in that sense, right? But that'd be the way I do it. Just saying, put them to where they could be comparable, which is just marginal by itself. Good question, though. Other questions? All right, I'm going to do this slide. We'll go and break. So we're going to use this Lavon package for using multivariate models with maximum likelihood. You read in, I think, chapter 2 and maybe a little bit in chapter 3 about robust maximum likelihood. Lavon allows from, or has a robust maximum likelihood estimator. That robust refers to data that may be not exactly the right amount of platet or leptokurtic, like how much flat or thin the tails happen to be of your data, right? So it corrects for that. So it still doesn't correct everything. It's not robust to using binary variables and calling them normal, right? I'm going to talk to you, and as I put this slide in, I was like, okay, I can't assume any of you have seen Lavon before. I bet some of you have, maybe many of you have, but I can't assume it. So now I'm going to talk to you about Lavon. I'm going to try to combine the two. How Lavon works, and then how that maps onto our maximum likelihood and multivariate normal. Okay? With that, we'll pause, come back in about 10 minutes. The exciting conclusion. Yeah, I know. Sarcasm. Okay, so let's talk about Lavon. How many of you have used Lavon before? Who hasn't? Everybody has. Let's assume that those who may not be here may have not. So I'm going to have to cover this and we'll go quick, okay? As you know, Lavon uses character strings to specify a model in R. And then you submit that long character vector into a function, and Lavon parses it and creates a model for you, right? The function that you submit it to can be SEM, could be just Lavon, and could be CFA. How many of you have used the CFA or SEM versions before? Anybody used the Lavon version before? Lavon, if you use the Lavon version, you got to specify like everything. CFA and SEM make assumptions about some of the model parameters that you may not want to specify. I'm going to use, well, I think I have SEM on this, but next week or the next time we have a meeting, 2 weeks from now, I'll have the Lavon function. We'll specify all the parameters. So here's an example piece of syntax. And if I flip over to R, see this here. Everything in RStudio that's green is a character, but Lavon syntax works by taking variable names from the data file that you have. So I called I'm going to model the missing at random data for performance. And the way I'm going to model it is based on IQ. So this is not a multivariate distribution just yet, but it's about to get to one, okay? So IQ is named to the data set IQ. Here, let's just show you this. IQ is spelled the same in my data as it is in Lavon. Perf_mar, performance missing at random assumption, is named the same as well. So that's what Lavon will look for. So this is what a regression looks like in Lavon. Perf_mar tilde. So thing on the left side of the tilde is your dependent variable. The thing on the right side of the tilde, the one there is often not put if you use SEM or CFA. Those fill it in for you. If you use Lavon as a function, it does not, and it gives you a nice warning about it at least. Hey, there's no intercept. But one refers to the intercept. And there are times in your life you may want to do something with the intercept. Like in a confirmatory factor model, you want to look for scalar invariance. You got to make constraints on your intercept. That's how you note it in the syntax. So this is a linear regression. You can think of, we're going to have an intercept and a slope there. Our variables are separated by a plus. That looks almost like a linear regression should. It's straight LM style syntax for regression. So far, so good. So in this model, we know we have an intercept that's sort of inferred by this a slope that's inferred by this part. One last thing is the residual variance. So when you take a variable and you put 2 tildes, the thing on the other side is the covariance. The covariance of a variable with itself is just its variance. So here, perf_mar will have, this will tell it estimate the variance of it. But note, we don't usually call this the variance in the case where perf mar is being predicted. This is the residual variance. It's what's left over. So what this is specifying is that simple linear regression model that I started notating in my notes document by hand, first part of class, right? That's what this is giving us here. So then I can take this, run the analysis. I'm leaving mimic m equals m plus in. You may wonder why, because I tell you you should use Lavaan. Well, what mimic equals m plus does is it sets the constraints from some of the assumptions that m plus uses and puts them into Lavaan to run that way. Part of that is which variable is part of the log likelihood function. So when you run this here, there's no way of telling if IQ, for instance, is assumed fixed or is part of the likelihood. And that's the hard part of the Lavaan. Have you ever considered that when you did Lavaan before? Those of you who have? Do you know which variables are entered in the likelihood versus which aren't? Hard to tell, right? So for us here, m plus will give us a series of pretty standard assumptions where we would have to specify a model for that variable for it to be part of the likelihood function. There are some other features with it, with m plus, but I'm not going to focus on those. I believe other features with it. I don't know enough. But mimic equals m plus is what I will use. Estimator equals MAR means, MLR stands for maximum likelihood robust. So that's our robust maximum likelihood estimate. We estimate this, and now we can see our summary. Let's try that again where you can see it better. Whole bunch of stuff at the top. We have 20 observations, and actually if I do this way real quick, I take this off. Nope. No. Anyway, I'll leave it there for right now. So when I started using Lavaan and started teaching Lavaan, first of all, I don't usually use Lavaan in a lot of my research. My research, I end up building my own stuff usually if I have to. But as I'm getting into the nuts and bolts for this class, I'm like, oh, things have changed. But here's what I wanted to tell you. Here, the number of observations used is 15, total is 20. That is one of your clues. IQ is not in the likelihood. Otherwise, it would have used all 20, or it wouldn't have told you about it. All right? I'm going to scroll on down past this. I have some slides on that later on. The other thing I want to note is information. Standard errors are based on the sandwich formula. I know Craig Enders talks about that. Sandwich formula is a robust or generalized estimating equations, helps for standard errors based on dependency and data. The information matrix is the center of that. So that's why they call it the bread, the sandwich. And it is observed. And it's observed information based on the Hessian. So now all of those terms you read about, now we're going to sort of talk about, right? That's how Lavaan is doing this. So what you would know is if you had all variables in this analysis in the likelihood, this would be ideal because you're using observed information, Hessian, sandwich estimators for the standard errors, and then all the data. But it's not ideal because you're not using all the data. And therein lies what I need to teach you. How do you know that you're using all the data? That's tough. Have you thought about that when you use Lavaan before? I'm looking for a new angle to get you to see Lavaan in a different light. Maybe? Anybody? No. Okay. All right. But let's look at our estimates here. We would say that job performance goes up by 0.15 for every 1 unit increase in IQ. Now, 1 unit increase in IQ refers to literally 1 IQ point, so 100 to 101. So we can't really tell, that's 0.15, is that really meaningful? I don't know, right? We have a standard error, you know where that comes from. And, well, I'll leave it at that. Our intercept's negative 5.114. And our residual variance here is 0.4373. And if we really wanted to fix this, we can have Levon tell us how much variance accounted for that is. So our R squared is 0.4. Pretty good, right? Sounds pretty good. I was going to start by comparing these results to OLS regression real quick. And here, let's see if I can compare and contrast side by side here. So now, take a look at our values. First thing, the regression slope, 0.150 versus 0.1496, right about the same. Our standard error is 0.054. The standard error here in OLS regression, 0.050. So those are different. Now, it's different in the thousandth place, but they're different. Why are they different? Why do you think?
Is that because ML is using n just n instead of n minus?
Yeah, the standard error. So there's several reasons. Let me start. In a typical OLS regression, who wants some more matrices? I see the eye roll. It's cool. I like it. What if I told you I could do our matrix of standard errors, right? Our matrix of standard error squared in this case is sigma squared times x transpose x inverse, where x is your design matrix. Probably seen that before. That is least squares, right? And this means that sigma squared is divided by n minus 1. So yes, that is a contributing factor. Our sigma squared is too big, and that's part of it. The other part, so that is why we would be, our Levon standard errors should be, you would expect them to be a bit smaller, right? Like underestimated. But contributing to this is also we're using robust maximum likelihood, and we're using sandwich estimator for our standard errors, and so that's readjusting them. But that's part of it. So what we see is in least squares, we actually have a smaller standard error than in ML in this case, and that's partially because of our use of MLR and partially because of the standard, the robust ones. In fact, if I wonder what happens if I did this. Now our standard error is 0.047. So we turn off MLR and we do get it smaller, 0.47 versus 0.54, right? So that is because of the difference in what MLR is doing, leptokurtic, platykurtic versus our data. Right there. Okay. Is this the MLR version? Yeah. All right. Okay. So going back to least squares, though, also note that our standard error is 2.246. We square that, residual variance should be 5.04, and Levon we estimated to be 4.373. So that's the ML effect right there. Right? Our point estimate of our variance is too small because we're using ML and a small sample size. How's that with everybody? Everything okay? All right. So at this point, after we started showing this in the chapter, I was like, all right, I'm going to dive into the EM algorithm. I'm not going to do that today. Can we just stop on the EM today? Would that be all right? Let me just go through the other bits of Levon and get us started with what's in Levon from a multivariate models perspective. And then we can go back and talk EM algorithm and factorized regression next week or 2 weeks from now, okay? So I'm going to skip ahead to multivariate models itself. So, I like to approach path analysis from this idea of multivariate models. I give this example to you to begin class. If we have these two outcomes, we're predicting them and we're doing it simultaneously. That's what I would call a multivariate linear model. Path analysis is a step a little bit further along than there, and I'll talk about the differences in just a moment. They all fall under what he calls the SEM framework, which is basically multivariate normal doing everything. But to the SEM folks, they go beyond that too. So in classical multivariate textbooks, we often have a chapter about multivariate ANOVA and multivariate regression. And when these methods were first developed, they used least squares. That was our method of estimation up until maximum likelihood theory and computers really came in. Least squares estimation, as you know, listwise delete, so it's not good with missing data. It also had very limited methods of setting what the estimates for the covariance matrix happens to be. So when we get to multivariate models, when we have two outcomes, each outcome will have a residual variance. But it's possible there's a residual covariance, which describes how far off we are in each in a similar direction, if the residuals are correlated, right? When you have more than two, that matrix gets very large, right? For every variable you add, you have to add its covariance with all the other variables in your data. So it gets, number of parameters gets very large very fast. And back in classical multivariate statistics, you would have something they would talk about with the assumption of something called compound symmetry or sphericity, which is a very simple version that you can do with least squares. And then they don't. They say, oh, that would usually fall under the heading of repeated measures ANOVA. You remember that. And then the alternative to that was MANOVA. And depending on who taught it, I know I didn't do a good job when I taught it. The matrix that goes in there basically says you're estimating every residual covariance. And then when you get to mixed models, there's places that are in between. So this is less the point of this class, but there's very few methods allowable in classical multivariate between those two, right? You've got compound symmetry on one side, general that just estimate the whole thing on the other, MANOVA. So the other thing you wouldn't get is information about model fit. Well, it turns out when you have multivariate methods, you also have to now assess how well they fit your assumptions of the model. One of those assumptions is how well your data resemble, your model resemble, the results resemble the data that went into it. So what I'd like to say is all of our classical methods that I mentioned there, MANOVA, repeated measures, and so forth, are now incorporated or subsumed into the SEM framework, Bayesian frameworks, or other methods. And pretty much every result you had before, like, how many of you have learned Wilks Lambda? Remember that? It's a multivariate hypothesis test testing mean vectors across multiple groups. You can actually run like LME and take a likelihood ratio test, rescale it, and show that it's Wilks Lambda in certain cases. Right? So a lot of the multivariate models and the things that we started with have really worked their way into something that's much more general and much more flexible for data these days. So how are we doing? All right. So we're going to talk about path analysis models using structural equation modeling software. There are other paradigms. I mentioned mixed models, the LME package, Bayesian networks. You may have ever heard of Bayesian networks before, BayesNets. We see them in small corner psychometrics that I reside in. But they're basically graphical models, which is another version of a path model that falls under that umbrella too. You also see them in computer science, Judea Pearl, his work, so forth. So these are all linked together, is what I'm saying. I'm giving you the kind of the path analysis version of what we have here. The theory behind each is pretty much identical. The main difference is software, right? Like M+, probably the most complete for having a bunch of options, but no piece of software does everything that you'd want in a multivariate model off the shelf. And that's where I envision the way how we play out with this course. I teach you how to do sort of the CAN package version, but also how to venture into your own. When something doesn't exist in software, I in the old day, we used to turn to the optim function in R or NL mixed in SAS. These days, I turn to Stan or JAGS, the Bayesian programs, because you basically have to specify the model yourself and have something else run it, right? The key and sort of the art of what we're doing is what I'm trying to teach you here. That process of specifying the model is hard, and I want to reinforce that in this class, right? How do you specify that model in a piece of software if you know that you can get mostly correct, Lingual, I bet this is a problem that fits what you've talked about without going too much into that. Things can be almost right with M+, or almost right with Lavaan, but frustratingly not right. Like, so one of my examples later on, I've got, again, that biological sex marker, female versus male, right? Clearly binary. If I stick it in Lavaan and do nothing, it assumes it's normally distributed. Bad idea. If I tell Lavaan, no, it's categorical, Lavaan then switches the estimator to something that uses and assumes missing completely at random. So it's frustratingly close to being what you need it to be. And so my job, the way I'm sort of envisioning the rest of this class is how do you take the models that you're used to, like Lingual, your model for your dissertation or your master's or whatever it is, and learn steps to how to implement it the right way, even if those steps would take a little bit more training or a little bit more practice. But that's my thought. Okay? So that's why it's frustrating. By the way, whenever I can put this character in, I love it, the interrobang, right? So we're going to start with path analysis today. Across all these models, the problem that we have is as we grow with the number of models or parameters in our model, the number of variables, right? The idea of going from univariate to multivariate, the number of parameters increases, and it may increase at a much faster rate than you anticipate, right? So the problems that creates are for small sample sizes, we may not be able to estimate the model at all, may not run. By the way, when a model fails to converge, it's a synonym for looking at the likelihood being very flat. You couldn't find the peak, right? So if you think about what we've taught about in this class, likelihoods that are really flat that may not have a maximum, thing doesn't converge, right? Missing small sample sizes like that. The other problem is the more parameters we have this need for extra data to be able to estimate all of them well, right? We talk about previously in basic statistics, we introduced the concept of the sampling distribution of the mean. And we introduced that to talk about how parameters themselves have error, right? And we sort of leave it at that and go on. But the sampling distribution of the mean is one thing. We saw from a couple weeks ago or last week when I did the maximum likelihood estimation software that the curvature for the mean was really tight for 5 people, really curved. So it had a smaller standard error. But if you looked at the dimension for what the variance was, it was flat, right? That's your idea that some parameters take more data than others to estimate precisely. And that's really the case when it comes to multivariate models. It's very difficult. All right. And then finally, in multivariate models, model fit is something we have to check. Does our model give us results that somehow resemble our data? That's the way you can think of model fit. Because in a multivariate model, there's nothing that stops, like for me, saying, hey, I don't care about this covariance between residuals of performance and usefulness. It's not part of my story. Everybody said that. That's not part of my research. It's not part of my story. If you work in statistical consulting, you hear people, oh, I don't care about that. That's not really part of my parameters. But yeah, guess what happens if you omit it, right? You omit it, and now other parameters start to be biased because the model doesn't fit. It's like, it's real easy to say, I don't need a residual covariance between 2 outcomes in a multivariate model. Yeah, but that may cause an inflation in or a deflation in certain parameters in standard errors, and that's a problem too. So multivariate models are complicated and messy. If I put this onto the book, think of it this way. When you get into the auxiliary variables, we're building a huge multivariate model. part of that model is the one that we wanted to start with for our analysis. And another part of that model is something to do with the auxiliary variables. And if you remember the path diagrams that were kind of being thrown on you in pages, all the auxiliary variables have these dual-sided arrows between them indicating all their correlations are being estimated. That's part of this problem too, right? So if you've got small sample sizes and missing data and want to use auxiliary variables, it's probably going to have a harder time estimating things, is what we're saying. Right? But that's where we're moving. So this has a name. Basically, there's a quadratic increase in the number of parameters as the number of outcomes increases linearly, right? So number of variables go in, parameters go up like that, right? And the name that I learned it under was something called the curse of dimensionality, right? The bigger number of dimensions, the bigger number of parameters, the harder it is to do things. So let's think a second. Okay, I mentioned this being the structural equation modeling approach. One of the ways around that, in part, although the number of parameters is equal, is to think about factoring a multivariate distribution into smaller components. So the factored regression approach. Although you still have the same number of parameters, it may be each component of that may make it a little easier to estimate some, although not necessarily. But that's, I'm trying to tie what I'm saying to the book as we go on. So you be used as an analysis model. A covariance matrix must fit as well as, really the core of all this, where model fit issues show up in multivariate models is often the covariance matrix of your data. And what we can show is in the maximum multivariate normal, we specify a model. It will imply a covariance matrix. You probably saw it if you've taken factor analysis. You've heard about the model implied, or model, I think Lisa calls it model predicted. I just call it implied. And then you've got your real data covariance matrix, and you've got to compare the two. That comparison assumes the real data covariance matrix doesn't have any constraints. It's saturated. You're estimating all the unique parameters in it, all the diagonal elements, all the off-diagonal elements. So, questions so far? Okay. The biggest difference from univariate models is model fit. In univariate linear models, there really wasn't a model for the variance because there wasn't much of a model. Sigma squared error was all you got. Because in the normal distribution, that's all that went there, right? And that means so long as you put a parameter there, it was estimated perfectly. Model fit was perfect. You don't have to worry about this. But because of the number of variances and covariances, multivariate models, we often don't saturate them, meaning we often don't either estimate them directly or have them become estimated through combinations of parameters. That latter part, what I mean is, there's a relationship between, for instance, a regression coefficient and a covariance, right? So, or a correlation, right? So if you have a regression coefficient, it sort of does the job of a covariance. So you could say X predicts Y and get your coefficient, regression, or you could say X and Y are correlated and get your covariance. And you can show, using the standard deviations of X and Y, that you can transform one to the other, right? So often what happens is when I say that we don't have fully saturated, it means we don't have a place to put each of our parameters that doesn't fit onto the covariance matrix. So any non-saturated model for the variances must be shown to fit the data before being used for interpretation. Basically, we have a new step in the analysis. We got to check model fit. And that applies when you use the structural equation modeling approach for this, we do too. Because if it doesn't fit, that's just as bad as using MCAR or something else too. Gosh, there's so many different catches with data. All right. Can't we just use ChatGPT? All right. Here's our example data set. I generated this many years ago. It was based on a paper. You can find the paper. Pajares and Miller. It's a nice path model. 350 undergrads. And set of women, set of men. I knocked out 10% of the variables. Actually, in the original data I had missing at random. I modified this to be, I'm sorry, originally I used missing completely at random. Actually modified this to be miss at random, and we'll talk more about that next time. So I'm using this data because I want to do something different from the book to give you something to generalize with rather than just follow the book's data itself. So I'm still mapping what the book concepts is to this, and that's where the problems of this week for this lecture have really materialized. But I will note that if you go and grab this data, if you go take the study and you look at like the results, my results and their results aren't going to be the same, mainly because I'm sampling a new set of data itself, right? Not only that, I'm simulating data with a multivariate normal distribution, but some of the variables had boundaries that, like, you have a limit, you have an upper limit to number of items on a test, or you have a floor or a ceiling, right? So they're not exactly matching. These are all the variables in the data. Real quickly, we have the sex of a person. Coded as female, so 1 means female, 0 means male. Most of these are going to end up being our auxiliary variables later on. But I'm going to highlight today, I'll just mention these and we'll come back to them later, okay? They collected math self-efficacy, a scale on how well you feel that you can do math. Perceived usefulness of mathematics, we're going to actually model that as an outcome today. Another scale. Math anxiety, another scale. Math self-concept. I don't know how that scale works, but that's in the data. I don't know what your math self-concept would be and how that's different than self-efficacy, but that's not for me to decide. I just do the numbers, man. Prior experience at high school level. So how many math classes you take in high school? Prior experience at the college level. So courses taken at the college level. And then finally, math performance, an 18-item multiple choice test where this is the total correct number of correct responses. Simply added together. Not the way we would ideally do it, but we'll leave it for there. Okay? All right. So we're going to begin with the multivariate regression model. We're going to predict performance and usefulness through two predictors in their interaction. The female-male variable, the sex variable, and college math experience, CC. So we look at our equations. We've got performance has an intercept, has a slope. By the way, I have to start putting commas in my subscripts to tell you this is the intercept for performance. Beta 0 comma perf means that's the intercept on that regression line. Beta 0 comma use is that intercept on that regression line. So there's 2 regressions here. Here's our female indicator. Again, their slopes. This is college experience. And then we have the female by college experience interaction on both. We also here have 2 errors, residuals. And you'll note there's 2 of them. So extending our univariate regression assumption to multivariate would make these follow a multivariate normal, or in this case, bivariate normal distribution. And similarly, before, the means of these errors are almost always 0. You change the mean of error to not be 0, weird things happen to the rest of your model. So we leave that at 0. And the covariance matrix now has a residual variance for performance, a residual variance for usefulness, and now a residual covariance we must estimate for performance and use between the residuals of performance and usefulness. Note that these are not covariances in our data. Remember that, right? These are covariants of what's left over after we predict the results. How are we doing? All right. There's our data. And because Lisa Hoffman, I have to live with my wife. Got to send her CC at 10. Okay. The scale goes from 0 up to 40 or something like that. These are the number of credit hours you've taken in math classes in college. And I think the average was right about 10. So that's what I did. All right. So the variables analysis and path analysis, we make some distinctions. And you'll see this in Lavon software, and I want to talk about it now. The difference between endogenous and exogenous variables, right? Now, why that matters is in part what assumptions you're making about the variables, and that does tie to missing data. Auxiliary variables, for instance, we would call exogenous, right? Meaning those are variables whose variability is explained, variables that vary, that exist, but they're not explaining that variation in our model. We just take them for what they happen to be. So exogenous variables not being predicted. Endogenous variables, those are being predicted, right? So in our example, performance and usefulness, the two y dependent variables are endogenous. Any dependent variable is endogenous, we would call that. Exogenous variables, in this example, are on the right-hand side. They do not appear anywhere on the left-hand side. That means to make them endogenous, not only do they have to appear on the left-hand side, they'd have to be predicted by something. We can add variable to our model with an empty part to it. But anyway, so female and college experience are both exogenous variables in this example. So the difference between what I'm showing you here, multivariate regression, and full-on path analysis, is that in path analysis, some of the variables that are endogenous can also go and predict other endogenous variables. So what I mean by that is, if you think of a situation where CC right here is exogenous, but if we wanted to predict it based on someone's sex, female, it would also become endogenous at that point, right? And this is just more of a tabulation distinction, but the mathematics, if you go through the math behind path analysis, if you're looking for a good book for that, David Kaplan's books on structural equation modeling are fantastic. Lots of matrices, but very good. And then here's our path analysis model. So here's what we're describing. The terms in blue are our residual values. These are our coefficients of the model. And the terms in orange are the exogenous variances and covariances. Now, depending on your path analysis software, though, structural equation modeling software, depending on the options you put into Lavaan, the only two variables in the software may be the endogenous variables. That's how M plus defaults to. So mimic equals M plus is going to only put these two variables in the likelihood. But if you want these variables in the likelihood, you have to work a little bit harder. I can show you how to do that. Right? Now, if you're doing this in Amos, I think even in Stata's, whatever Stata's path analysis thing is, CM thing, I don't know. Can't help me there. These are part of the likelihood by default. Right? So there are many different packages that say, oh, all the variables are, but there are some packages that say only endogenous variables get entered. Okay? And that's one of the keys to knowing what to do. It's R's version of the labels. So here, I'm going to show you that I plug this in. I started building this a little bit differently, but I've got syntax where I've got performance and usefulness. They are the regressions. I put 0 slopes on the female CC10 and female bi CC10. And believe it or not, back when I first built this example, before I came to Iowa, this would enter each of those three variables into the likelihood. It now does not. So more on that in just a bit too. But here you see I'm specifying a spot for each of my parameters. I have my residual variances of my dependent variables right there, my endogenous variables, and I have my residual covariance. Okay. Why you need potentially all variables in your likelihood is if you want to do a likelihood ratio test between this model, where there's 0 coefficients, so basically this is a multivariate empty model, and one with the coefficients, the data would have to be the same. The data used by the software would have to be the same. So you have to make sure that if you have missing data on all of these, the n size is the same to do the likelihood ratio test. Same observations to be able to make it work. But yes, here's what it tells me when I do that. 181 cases were deleted due to values in exogenous variables. But you can fix it. Here's the fix. I'll get more onto the fix next time. What is the fix? Actually, I'll tell the fix now. I'm estimating the means, and I fixed this today, but not in my slide, the variances and covariances of all of our exogenous variables. Once I estimate them, they become part of the likelihood. But that's neither here nor there. When I do that, I have now built a 20 parameter model for this model right here. Right? I have, if you think about these 5 variables that are in the likelihood, when I bring these into the likelihood, 5 variables, right? It's going to assume multivariate normal, even though it shouldn't, particularly for the interaction or for the female variable. But it is. And with 5 variables in a multivariate normal distribution, that means I have 5 means. If I were just to estimate that multivariate normal distribution, there'd be 5 means, 5 variances, 10 covariances. So 20 total parameters. But my model that I just put up there doesn't have 20 parameters. It has 11, right? I didn't add the regression slopes, so that's one of them. I have 5 intercepts, 2 residual variances, 1 residual covariance, and then the exogenous variables, right? So what Lavaan will do is actually estimate 2 models for your analysis, right? It'll estimate your model, and it'll estimate a model that's saturated. By saturated, I mean this model right up here. Now, it's not going to report the parameters of the saturated model, but it's going to use it to help you with model fit. And of course, wouldn't you know, I have a typo on my slides. This should be 14 parameters right there. Come on, Templin. All right, so 14 parameters, 5 intercepts. Basically, the difference is we don't have 6 regression slopes, right? So what do we end up getting? We get results. It's going to talk about H0 and H1 in output. H1 is everything's estimated. H0 is your version, right? And the degrees of freedom it's going to report is literally the difference in number of parameters between saturated and your model. So what we're going to find is this gives me a chance to talk about model fit for 5 minutes. There's our results, right? 14 model parameters, 6 degrees of freedom. I'm going to parse this a little bit more as I go forward. So the first thing I like to do or talk about is with this analysis, we can actually come up with what the model implied covariance matrix should be for that 5-dimensional multivariate normal. And you'll notice a trend here, right? Our covariance matrix does not have values between our exogenous variables and our endogenous variables. And I believe this might be an older one, but these should have numbers here. And then the mean has a value for each. Now I will note what ends up happening, another part of the mimic equals m plus function is for these exogenous variables, where does it get its numbers, right? Are those dimensions that they search for in the maximum likelihood algorithm, or are they just plugged in from sample statistics? And I believe in M plus, they plug it in from sample statistics. But eventually, once you enter your variables into the likelihood, it will be estimated as part of the dimensions of multivariate normal. So that is that there. This down here is the H1 covariance matrix. So right away, you can already tell where we have 0 values for ours, there are non-zero values in the data. That's not good. We want our covariance matrix from our model to resemble this. Right. We can also tell for the values that are in the model, right? So here, look at the top corner. Compare that down with this. Those numbers are pretty close. That's pretty good. And if you look at the diagonal of the exogenous variables, those numbers are spot on, or actually not quite spot on, but pretty close. So if we take the difference between this, what the full estimated matrix is, and what our model says it should be, we end up getting something called the raw residuals. I hate that term, but there you have it. Just straight residuals. And those residual values tell you how far off you are for different parts. How far off you are for different parts will indicate to you where you need to go adapt your model to make it fit better. Right? So for instance, we're really, really far off on the covariance between performance and our college credits, right? But turns out, once we put in a regression coefficient predicting performance from that, there's going to be a number that goes in that spot in our fitted model matrix right there. And we'll get closer to it. All right, so model fit, how we examine it is, there's two versions. We call it global versus local. I'm going to fly through this. Maybe, you know what? Maybe I'll stop here. Give us a nice introduction at the next class about this. And then we'll dive into using Lavon for our various purposes for the SCM framework in his book. Okay? Questions for me? I feel like I'm wasting your time since you know Lavon. But I'm trying to tie this to what we're doing, so I promise. Yes.
I'm thinking about the relationship between the likelihood function and how we get some of the
Yes.
and we can use implement EM algorithms, right? Or iterative algorithms. Are those things used like, do we combine those things to likelihood function, or are we using only one at a time? Like depending on the data.
It's usually one or the other, but in some cases they can get combined. So when you're saying ML, when we don't say EM, when we say ML, we typically mean using like Newton's method or some optimization method to find the peak of this likelihood, what we call numerically with the computer. That doesn't involve EM at all. EM shows up under missing data, usually under missing data conditions. We hear about it in latent variable world, like the EM algorithm and IRT models. Well, guess what? Theta is missing. There you have it, right? And EM can be used, but we could still do ML with that. We would just have to marginalize across the missing data. That's tough. So what I mean by that is, maybe not in this context, but in like a latent variable model where you've got an ability predicting item responses. If we can write the likelihood and take the missing data out of it, we can still use Newton's method. And so we can still do that here too. We just have to integrate out of the data. Just not an easy thing to do. So when I say that is, you'll see like an M+, if you estimate M+ for latent variable models, sometimes in the output it'll say EM, and then sometimes it'll have a QN, quasi-Newton. Sometimes it'll say FS for Fisher scoring, which is another estimation method I didn't teach you. You can combine them, but they have to be the same approach. And usually in the case where we'd need EM, we'd need to go and integrate out what's missing to make Fisher quasi-Newton methods work. So in the case of this example, there would not be a really easy way to do both for it in one algorithm. So pick one and stay that way. That sound good? Long answer. Other questions? All right. Have a great rest of your week. Remember, nothing next week. Work on that reading quiz. Homework is due much later. You'll still have me back when I come. Also, no office hours next week as well, too. I'll send a note with a reminder. Thanks all. Have a great rest of your week.